Good morning, everybody. In this class, we'll be considering numerical integration and differentiation. So we start with this table. We'll commonly use derivatives. So I know you all know how to integrate and differentiate because you would have done that previously during the course of your study. So these are the different commonly used derivative. So you all know how to do this. So these are the analytical methods to differentiate, and for integrating, these are the this table shows the analytical method for differentiating. For integrating. In this lesson, we want to consider numerical integration because these methods, they are the analytical methods to integrate, to do your integration. But we want to make use of numerical methods. Numerical methods are approximate methods. So they are not like the exact methods. And we already know that numerical methods are suitable when it's not possible to get the exact solution. So there may be some complex functions that you may not be able to use these numerical methods to integrate. So we need to that you will not be able to use this analytical method. So these methods are the analytical methods. So there may be some functions that the function is so complex and it's not advisable to use this analytical method. So you need to find a numerical method to use. And so in this class, we'll be considering the numerical methods for integration. And the three methods we'll be considering are the Trapezoidal Rule, the Simpsons 1/3 rule, and the Simpsons 3/8 rule. The basic idea behind these methods, so they are called the Newton-Cotes numerical integration methods. The basic idea behind this method is that given that we want to integrate a function f of x from over the limit from a to within this limit. So the basic concept of this method is that in place of this function we want to integrate, we approximate the function using an nth order polynomial. So in place of this particular function that we are given and we want to integrate, we replace it with a polynomial f of n of x. So that's the basic idea behind the method. So for trapezoidal rule, you replace the function f of x with a first order polynomial. That's for trapezoidal rule. For Simpson's rule, Simpson's 1/3 rule, this polynomial that you want to integrate is approximated with a second order polynomial. So you have f1 of x, that's for Simpson's 1/3 rule. Then for Simpson's 1/8 rule, this function is replaced with a third order polynomial. So that's the basic concepts behind those three methods. So remember, we are trying to integrate this function over some limits. That's a to b or b to a. So the basic idea is to approximate this particular function using a first, second, or third order polynomial. And integration is summation. So if you're asked to integrate a function f of x, it's the same thing as getting the area under the curve. throughout the function. So for instance, if we want to integrate this function f of x from a to b, simply put, you are getting the area under the curve. That's just the as explanation of integration. We are summing over the area under the curve within the limits you want to integrate with. So for trapezoidal rule, like I said, you are replacing the function. This is the function. You're replacing it with a first order polynomial. And a first order polynomial from last class is just a straight line. So in place of the original function, you're just replacing it with a straight line within the limits of integration. That's for the trapezoidal rule. Then for the Simpsons 1/3 rule, you are replacing the function with a second order polynomial. I remember from last class, a second order polynomial, it has 3 points. The first point, the last point, then the point in the middle. So that's the basic, general structure of it. Then, because if you just use a straight line to approximate the function, obviously, even from this graph, you can see that the error, because when using a straight line, like this is the area is summing over, it's not considering this area. So obviously there will be error. So an alternative strategy is to divide the function you want to integrate into a number of segments. So here you have 3 segments. The function is divided into 3 segments. And you, for first order, for trapezoidal rule, you would use a straight line to approximate the function in between the segments. So this is a first order approximation of the function using um, using multiple segments. Then this is first order approximation because you're using a straight line to approximate the function over the number of segments you are interested in. But for this is zero order polynomial. This is zero order approximation. You are dividing it into a number of segments, but you are using a zero order polynomial uh, to break the function down into a number of segments. So this is the first order, breaking the function down into a number of segments, and this is zero order polynomial. Then here, you are not breaking it down into a number of segments. So for first order polynomial, you need 2 points, 1, 2, 1, 2, 1, 2. But for zero order polynomial, you just need just 1 point. So this is 1, 1, 1, 1, 1 point. So we start with the trapezoidal rule. So for numerical integration. So like I previously described, you want to integrate this function f of x over this limit from a to b. But for trapezoidal rule, you are replacing this function with a first order polynomial. So this is where the one comes in. The one being that is a first order polynomial you are using to approximate the function. Then if you can recall from the last lesson, in the last lesson we did interpolation and we did first order interpolation and second, third order interpolation. So if you can remember from last class, we approximated a first order polynomial. We derived this equation for interpolation using a first order polynomial. Then if you go back to your notes, you would see this exact same function when we're doing linear interpolation. So linear interpolation is simply first order interpolation. We derive this formula. So in place of this function here, we're just going to put in this formula here. and you are integrating within the limits from A to B. So in place of this function, you have this formula here. Then the result of the integration, when you integrate this function, you arrive at this. I'm not going through the proving of how you get from here to here. If you are interested in the proving, you can read the textbook. But when you integrate this, you arrive at this. So this formula here we derived is the formula for the trapezoidal rule. And it is called the trapezoidal rule because this is like the area of a trapezium. If you can remember from your algebra, the area of a trapezium is half base times height. So if this is the base, then this is the height. This is the height. FA plus FB is the height, and this is the half here. So that's where the trapezoidal rule comes from. And from here, this is the like a trapezium, and this is the base, and this is the height. So the height is, this is the ground level, and this is from here to here is the actual height. The difference between here and here is the height. So similarly for trapezoidal rule, you are replacing the function with a straight line because it's first order polynomial. So here is the base. So b minus a is the base. That's where this b minus a came from. Then the height is the average height is f of a. So f of a plus f of b divided by 2. That's the average height. So if it was a normal trapezium, is h minus 0 divided by 2. So that's where the half comes in. So that's h divided by 2. But here is f of a plus f of b divided by 2. So we got the trapezoidal rule based on the fact that the result of this integration is just like the area of a trapezium. So where this is the base and here is the average height. So we're going to use an example to reinforce trapezoidal integration, numerical integration. They want to integrate this function using numerical integration. So you all know how to integrate analytically. So that's not, but now this topic is like numerical integration. We want to approximate, we want to find an alternative method to integrate. The reason being that if you are given a complex function, so this function, we can just integrate it analytically and straight up we'll get our answer. But there are some functions that are complex, much more complex than this, and you might not be able to get the numerical integration. So that's what this topic is on. That's, you might not be able to get the analytical solution for the integration. So that's why we'll fall back on numerical integration. So we're asked to integrate this function from within this limit from a is equal to 0 to b is equal to 0.8. And so if you use numerical solution, this is the exact solution, but want to use trapezoidal rule. So equation 3 is the trapezoidal rule. So this is the equation 3 we want to use to find the integration of that function. So this is equation 3 here. So in order to perform numerical integration using trapezoidal rule, we are going to, so we have this function. So we already know a, which is 0. We know b, which is 0.8. So we just need to calculate for f of a and f of b. So f of a is simply f of 0. So this f of 0 is simply f of a, and this f of 0.8 is simply f of b. So we simply calculate for f of A and f of B. So we got f of A as 0.2, then f of B as 0.232. So we simply just put the results into this equation and we got 0.178. So remember that the exact solution, the analytical solution was given to us as 1.64. So we can track the error. So just by looking at it, this is the result of what numerical integration gave us. But this is the true solution. So we want to track the error. The error is very, very large. It's up to 90%, approximately 90%. And this error is due to the fact that this is the function, this particular function A. This is it, drawing it in graphical form. This is it. And for trapezoidal integration, you're using a straight line. So this is the straight line here. So this is the area below the straight line is what the trapezoidal rule is giving us as the integral of the function. But actually, the integration of the function is like the area under the curve. So this upper part is not actually covered for the first order polynomial that's using trapezoidal rule. So graphically, you can see the large error, which is very, very big because you're using a straight line to approximate the function. So you have a very, very large error. So I want to ask a question now. So you answer me from the chat. So what can we do? There are two ways we can use to reduce the error, and I've already made mention of it. So I'm asking a question. So what are the two ways we can use to reduce the error? Now, there are two ways we can use to reduce the error, or more than, if you know more than two ways. So can you answer my question? The trapezoidal will give us a very large error, but it's still useful. So I'm asking that how can we reduce the error, or what are the ways we can use to reduce the error? That's my question. So I want responses from the chat. So anybody? I'm waiting. I'm waiting for responses on the chat. How can you reduce the error? Okay. Increase the order of the differentiation. We can divide the surface into several rectangles, increasing the number of sets. Okay. So for all those people that have responded, okay, thank you for your response. Okay. So the ways we can reduce the error is to, okay, another person, we can divide the area into segments. Yes, yes. Okay, so thank you for all those people that have that replied. So all these comments you've made, all of them are all right. So the ways you can reduce the error is to divide because we are using like throughout the limit of the integration from 0 to 0.8, we're using a straight line. So one way you can use to reduce the error using trapezoid rule is to divide the function into segments. You divide it into segments. Then you use the segment division, you use a straight line to a linear line, or the trapezoidal rule to interpolate in between those segments. So this is what I'm explaining. So this is the function we want to integrate. What we were doing previously is just to use a straight line from the lower limit to the upper limit and just connect a straight line through, and it's giving us a very large error. So one way we can use is to divide the segment. Now we divided it into two. So we use a straight line from here to here. Then we use a straight line to approximate the polynomial from here to here. So here, using two segments is actually will give us less error compared to just not using any segment at all. So this area is not covered and this area is not covered, though it still reduces the error. But if we increase the number of segments, here we divided it into two segments, 1 and 2. So if we increase the number of segments into 3, 1, 2, 3, and use a straight line. So from this segment, you use a straight line, this segment, you use a straight line, this segment, you use a straight line. More area is covered and you have like less error. The more area is covered and you have less error. Then if you increase the number of segments to 4, 1, 2, 3, 4, and you use a straight line in between those segments, and use a straight line in between those segments. So you have less error, that's more accuracy. And so increasing the number of segments would reduce the number of errors. So that brings us to multiple segment trapezoidal rule. So we still want to use the trapezoidal rule because we think it's useful. And the way in which we do that is to increase the number of segments so that we can have less error. So we define a formula, h is equal to b minus a divided by n, where n is the number of segments. So n is simply the number of segments. Then b is an a. B is the upper limit and a is the lower limit. Then h is given by the step size. So for instance, if you want to divide the function into two segments, so this is your first segment and this is your second segment. So to get your step size, because the difference between this and this is your step size. Difference between this and this is your step size. So to get the step size, you use this formula. So if you wanted to divide it into, in this case, 1, 2, 3, we are dividing it into 5 segments. So if we wanted to get the number of step size, you just use this formula to get the number of step size. So going by this method now, we are still going to be using the trapezoidal rule, but now we're using multiple segments. We are breaking the function down into series of segments, and all we are going to do is that we'll integrate from the first segment, x0 to x1. We integrate from the using the second segment, x1 to x2, like that until you get to the last segment. So in this case, you would approximate the integration from here to here. So you do the integration from here to here. You do the integration from x1 to x2. You do the integration from x2 to x3. You do the integration from x3 to x4, then x4 to x5. you do the integration, then you sum it up together to get the integral of the function. So that's what explains this equation. And this equation is the same thing as this, because this particular integration using trapezoidal rule is approximated by this, where h is simply the step size. So h is b minus a divided by n. So this is your b minus a, and this is the average height. So this is the base, and this is the average height. So you are integrating, or you are approximating the integration from x0 to x1. So here is from x1 to x2, then to x minus 1 to xn. So this equation is substituting the formula of the trapezoidal rule. You are going to arrive at this equation. So there is a question: what does the step size do in the equation? So thank you for that question. The step size is to, this is the step size. The step size is to break down the limits of integration into smaller chunks. Because previously, if you're just using one single segment, there's no step size involved. It's just from, in the case of our question, from 0 to 0.8. But now, you are breaking down the function into segments. For instance, if you are breaking it down into two segments here, so this is your first segment and this is your second segment. So your step size helps you to know the limits of integration, because now you've, in the case of this exam, this highlighted figure, you are breaking down the function into two segments. So this is the first segment and this is the second segment. So now you cannot integrate from x0 to x2. So you need to break it down into smaller step size. So you need to break it down from x0 to x1. That's the first part. Then the step size for the first part is given by this equation. So you're not going to use b minus a because you are not integrating over the limits. You are breaking down the limits now into step sizes given by h. So you need to do the integration over this step size, because it's not all of this, it's not all these limits you are using for the first part, and it's not all of this you are using for the second part. So you are starting from here to here for the first segment, and you are starting from here to here for the second segment. So for your first segment, the step size is simply x1 minus x0. Then for your second segment, the step size or the width, you can just call it the width of the integration, is x2 minus x1. So the step size or the width, because you are breaking it down, you are breaking down the function down into some number of segments. So definitely you need a limit over which you are going to integrate, and which is given by the step size, because you cannot use the original step size. So that's what you need the step size for. So as we're going to do another example, so you're going to understand better. So this particular integration is given by this, using the trapezoidal rule. So this is the trapezoidal rule here. So FA plus FB. So in place of B minus A, so B minus A is like, just for one single segment, we are going to use this B minus A here. But for when you are breaking it down into multiple segments, so in place of this B minus A, you have a new step size. You cannot use the old limit of integration. So the result of what you got here is your width of integration, or is your new limit. over which we are going to integrate for the step size. So that's why we need the another width of integration. So this particular, the highlighted equation is the result of this integration using the trapezoidal rule. So this, the result of this using the trapezoidal rule, and that. So when you group the terms together, so when you combine all of these terms together in a more compact form, we are going to arrive at this equation. This equation here is the trapezoidal rule for multiple segments to do the integration for multiple segments. So you can see the illustration here. So if you have this function and you want to integrate over this function, so h is your width. This is the step size. Because if to say we are just using one segment, you are not breaking it down into number of segments, you don't need this step size because it's just from the lower limit to the upper limit. But now you are breaking down the function down into number of segments. So you need to be able to get the width of the integration. So the step size is also the width of the integration. So h is given by b minus a divided by n. And since you are breaking, since h is the same throughout, so the difference between here and a, here and here, here and here, here and here, here and here, and the last one, they are the same. You have the same h. So when you add this h together, this h, this h, this h, this h, and the last one together, you are going to get your limit of integration. So simply put, you need to, because you are breaking it down into number of segments, you need to have a new width of integration over which you are going to perform your integration. So that's the step size. So this equation, putting it into a more general form. So h is b minus a divided by n. And in place of h, if you put b minus a divided by n, you are going to arrive at this equation. So this equation and this equation are the same thing. It's just that in place of this h, which is the width of each segment or the step size, and is given by this. So this equation and this equation are the same thing. So what this equation is saying is that if you want to use trapezoidal rule for multiple segments, you just use this equation. You evaluate the value of the function. So you want to integrate a function using trapezoidal rule with multiple segments. You evaluate the value of the function at the lower limit, which is x naught. You evaluate the function at the upper limit, which is xn. Then you evaluate the value of the function in between the upper limits and the lower limits specified by your step size from I is equal to 1 to n minus 1. Then there is this factor of 2 there. Then when you do this algebra, the result is going to give you the approximated value of the integral of the function you want to calculate. So let's do an example to reinforce the concept. In this example, we want to use a two-segment trapezoidal rule to find the integral of this same function. So that's the same function in the previous example. So we want to divide the function into two segments now. So we don't just, because we want a better, we want to reduce the error. So here now, n is equal to 2 because we have two segments. Then our width now, or our step size, or the width of the integration for each segment is given by this formula, which is 0.4. So that means that, so given this equation, So this is the equation we're using for multiple segments. So from the equation, we need the value of the function at the lower limit. And the lower limit is 0. So f of 0 will give us this value. Will give us this first value. Then f of x of n, that's the last value, is f of 0.8. So we need this f of x of I. Then how do we do it? So this is the general formula. In this case, our n is equal to 2. So based on this general formula, now, since our n is equal to 2, we know that we need to get f of 0. We need to get f of 0.8, which is the last limit, which is the upper limit. Then we need to get f of x of I. And from the formula, it says that is the summation from I is equal to 1 to I is equal to n minus 1. So you start from I is equal to 1. So I is equal to 1 is simply f of x1. So that's why we have this f of x1. So you are summing from I is equal to 1 to I is equal to n minus 1. But in this case, you are summing from I is equal to 1 to I is equal to n minus 1. In this case, n is equal to 2. So 2 minus 1 is 1. So that means that you just only have f of x of 1. If to say our n was 3, then it's going to be a summation from I is equal to 1 to 3 minus 1, which is 2. So there's going to be another plus here. So I'm just saying that if n was equal to 3, if it was not equal to 2, there's going to be another plus here. But in this case, it's going to be f of x of 2. Then this one is going to be f of x of 3. Since n is 3, the last one is x of n. So if n is equal to 3, this formula will reduce to this formula. But now our n is 2. So we just revert back to this. So we have already known f of 0 as 0.2. So we need to calculate for f of 0.4 because f of x1 is simply f of 0.4. So we need to calculate for f of 0.4. So how did we get this 0.4? We know that f of x naught is this, is x0, which is the lower limit. We know that f of the lower limit, the upper limit is 0.8 because the upper limit is 0.8. So how did we get this 0.4? So we got this 0.4 from the step size or from the width. So when we calculated for the width, we got 0.4. So is this 0.4 we are getting here? So join me in the next using the same link.